Okay, what is a router and how does it work? A router is a device that joins two or more networks and passes packets from one network to another. A router can do the following things: connect to similar networks like LANs and WANs, interpret layer 3 addressing, and determine the best path for data. We'll talk a little bit more about how they do that in a bit when we talk about routing protocols. But the key thing is they route traffic. Here we have a few examples of different routers. This would be like a home consumer grade router. This might be a business grade router, and this is an example of what you might see at an ISP. One important thing to note is oftentimes these can have the functionality of a modem or a switch built into them. There are three categories of routers that we want to talk about. Core routers, often called interior routers, and edge routers. Those are often called border routers. And then we want to talk about exterior routers. Core routers are inside our autonomous system. Edge routers connect to the outside world. Exterior routers are routers that do not belong to us. Usually they belong to an ISP. Routing table. There's a ton of depth to routing tables. I'm going to try to give the most basic, quick overview to routing tables that I possibly can here. A routing table is essentially a list of paths to various networks required by routers. This table can be built manually or automatically. These are the parts commonly associated with a routing table. We have destination, gateway, GIN mask or subnet mask, sometimes called net mask, flags, metrics, ref, use, type, and interface. Destination. Essentially, this is every network ID that is directly connected to this router. Gateway. This is essentially where the packet should go. Where is it going to be forwarded to? The next hop in the list. If we have a star or sometimes onlink or 0.0.0 here, then that usually indicates that there is no gateway needed. GIN mask. This is essentially just the subnet mask or net mask. Flags. This just means the link is up. If it's a U, the route is up. If it's an H, it means it's a host. If it's a G, it means it's a gateway. Type in interface just to indicate what type it is and what interface it's going out. We'll go ahead and talk about routing metrics on the next slide and then in a little more detail throughout the rest of this video. When there's more than one route to get to another network, we'll use a metric, or routers will use a metric to determine which route to use. The lowest value metric is the one that's selected. Here we have an example of some metrics that can be used. Just a quick note, not all of these will always be used by every single routing protocol, and some of them will be weighed differently when they are used. This is just an example of some of the metrics that can be used. Hop count. Hop count, the number of routers a packet passes through on the way to its destination network. Bandwidth, our connection speed. Delay, the amount of slowdown or the relative latency that we're dealing with. Cost. This is usually administratively assigned to specific links. So this is something that is often manually assigned by an administrator. Let's talk about dynamic and static routing real quick. When we're talking about static routes, these are something that are almost always manually entered and then they won't change automatically. Here on the slide, it says routes never change, but the idea is that they won't change or update automatically. Whatever they're configured, whatever is manually configured is often what is going to stay in the routing table. You can sometimes have routers that will detect their routes on setup and then they'll stay static again until someone manually changes them. So they won't change automatically or update automatically on them. That is a static route. However, most routers also have the capability to update their routes dynamically. Dynamic routing. It's a process routers use to update their routes automatically. There are a variety of strategies used, and we'll talk about some of the different routing protocols and some of the ways they try to optimize and find the best routes on their own. When we talk about routing protocols, it can get pretty complicated pretty quick. I think this graphic is a good way to visualize everything that's going on because there's so many different routing protocols and categories and subcategories. So right now we're focused in on dynamic routing protocols. We break those into two major categories: interior gateway protocols and exterior gateway protocols. We call it interior gateway protocols, IGP, exterior gateway protocol, EGP. So let's talk about exterior gateway protocols first because it's fairly simple. We have one protocol that we pretty much use in the modern era, BGP. That's pretty much the only one you're ever going to see. So just to be clear here, when we're dealing with edge routers that are communicating out over the internet, They are almost exclusively going to use BGP, Border Gateway Protocol. This is sometimes called a path vector routing protocol, or other times called a hybrid routing protocol. For interior gateway protocols, inside an autonomous system, we have a whole variety of different protocols that can be used. One category is distance vector routing protocols. We have another one called link state routing protocols, and then we have one called hybrid routing protocols. These are the routing protocols that fall into each category. Let's start with distance vector routing protocols, RIP1 and RIP2. Distance vector, a set of routing protocols that calculates the total cost to get to a particular network ID and compares that cost to the total cost of all other routes to get to the same network ID. So the key thing we're worried about when we're talking about distance vector routing protocols is how many hops. What is the primary distance? Now, an administrator can manually overwrite that. It can manually set a specific distance to a metric of 1 and make it prioritize that, or 10 to make it avoid it, or different things like that. However, generally, when this is working dynamically, automatically, the routing protocol will count how many hops for each different path that it has to get to a destination, and it will choose the one with the least number of hops. The first and oldest routing protocol is RIP, the Routing Information Protocol, RIP version 1. These are the type of things that you'll see pop up on quizzes or exams all the time. It's a distance vector routing protocol. It's the oldest protocol, dating from 1960s and the 1980s. The maximum hop count is 15. It takes every 30 seconds, it sends out an update request. This can often cause overloads on larger networks, so this really isn't suitable for big networks. It's not scalable. RIP is not scalable. It does not support VLSM, no variable length subnet mask support. It has no authentication, at least in version 1. So RIP version 1, no authentication. RIP version 2 does have some authentication. We'll talk about that here in a second. But essentially, it was very easy to attack a network. You could just send out a fake routing table, and everyone or every router on the network would just inherently believe whatever you tell them. The key advantage was it was extremely simple, simplicity. Here are some disadvantages: limited metrics, excessive overhead, poor convergence time, limited network size, and slower and less secure. RIP version 2. It's Routing Information Protocol version 2. It's the current version of RIP. It was adopted in 1994, so again, quite a while ago. Fixed many problems with RIP version 1. VLSM support was added, authentication was built into the protocol, and most routers today will still support RIP version 2. Okay, that covers all of our distance vector protocols that we're going to talk about, RIP version 1 and RIP version 2. Let's jump over here to link state routing protocols. We're going to only talk about two main ones, OSPF and ISIS. Link state routing protocols. It's a type of dynamic routing protocol. So again, it's a type of dynamic routing protocol. Routers possess information about the complete network topology. So each router will attempt to map the entire network topology. Nodes independently calculate the next best path. So each node, each router will independently make its own decision about what the best path is. Link state routers will generally only announce changes to the routing table. They will not constantly broadcast the entire routing table or attempt to update the entire routing table. OSPF, Open Shortest Path First. It's an interior gateway protocol and a link state protocol. It can scale to large networks. It's often not found on cheap home routers, so very rare for cheap home routers to include this protocol. However, most other routers on a professional or enterprise level will have OSPF. I believe it is one of the most common used routing protocols for interior gateway, the most commonly used interior gateway protocol. Requires a great deal of computational power. It supports authentication. The shortest path first method prevents loops. So we prevent loops naturally with the method that it uses to calculate the best route. OSPF uses more complex algorithm. So whereas distance vector protocols tend to only be concerned with the number of hops, OSPF will use a variety of metrics to try to determine the best route. So it'll take into consideration things like bandwidth and try to calculate which route is going to be faster overall. Low overhead, fast convergence, and fairly stable. The other link state routing protocol that we're going to talk about is ISIS, intermediate system to intermediate system. It's very similar to OSPF, and then it has a best path algorithm where it uses a variety of metrics to try to calculate which route is going to be the best overall. It sends only updates to routing tables. So again, it's not constantly trying to update the entire routing table. It just checks for things that are changed once it's mapped the network. It works with IPv from the start. So again, both OSPF and ISIS currently support IPv6 and IPv4 in their current versions. ISIS is often used as the de facto standard for ISPs. So internet service providers tend to prefer ISIS. It's because it's slightly more scalable than OSPF. Again, don't be confused. OSPF is still scalable. We generally consider it scalable. Just at the largest levels, ISIS is slightly more optimal for that. Hybrid routing protocols are essentially a combination of distance vector routing protocols and link state routing protocols, or at least they have elements of both, and that is why we call them a hybrid routing protocol. There's only one hybrid routing protocol under the Interior Gateway Protocol umbrella, and that is EIGRP. Okay, again, EIGRP stands for Enhanced Interior Gateway Routing Protocol. It is sometimes referred to as a hybrid routing protocol. Other times it can be referred to as an Advanced Distance Vector Protocol. So it may come up as a hybrid routing protocol or an Advanced Distance Vector Routing Protocol. Again, it has aspects of a link state routing protocol and a distance vector protocol. Fast convergence time, low network overhead. Easier to configure and less CPU intensive than OSPF. But again, OSPF, last I checked, is still one of the most popular routing protocols that is used. It supports multiple protocols and limits unnecessary traffic between routers. It was designed by Cisco, and originally it was a proprietary routing protocol, but eventually they opened it up for everyone to use. Okay, that covers distance vector routing protocols, RIP1 and RIP2, link state routing protocols, OSPF and ISIS, and hybrid routing protocol, EIGRP. We're going to cover the BGP Border Gateway Protocol, again, our only exterior gateway protocol. It's not the only one that can be used, but it is realistically the only one that is ever going to be used in most situations. So if you ever see an exam question that's talking about exterior gateway protocols, it is probably going to be BGP. Internet growth in the 1980s required an update of a kind of standardized dynamic routing protocol. So we wanted a standardized dynamic routing protocol. These are the three organizations that oversaw that: the Internet Society, ISOC, the Internet Assigned Numbers Authority, and the Internet Engineering Task Force. On the CompTIA exam, BGP can be listed as a hybrid routing protocol. Technically, it's a path vector protocol, but again, oftentimes you may hear it referred to as a hybrid routing protocol. Here is the key points of BGP listed out. It's the one protocol we use to communicate between autonomous systems. The current version is BGP4, connects all autonomous systems, implement and support route aggregation, determines the best path based on different factors. So again, we're using a variety of factors. It is the most complex of the routing protocols. Not all of the routing protocols communicate with each other very nicely, so we have to use something called route redistribution. It's where a router takes a route that is learned by one method and announces those routes over another protocol. Administrative distance is a feature that we use to determine which route is going to be more reliable when we use multiple routing protocols. The last thing I want to talk about before I close out this video is a multi-layer switch. So generally when we talk about a switch, we think of a layer 2 device. A switch is a layer 2 device, operates at the data link layer, deals with MAC addresses and frames and that sort of thing. However, there are more advanced switches that operate at higher levels. So my advice is that generally whenever you hear the term switch, we're thinking of a layer 2 device. However, if you see the term multi-layer switch, you know that you're dealing with higher levels in the OSI model. Okay, that's all the information I have for you. I hope you found this video informative, and I hope you have a wonderful week. Bye.